Morning, everyone. How are you doing? Questions while we wait for people to come in? Morning, Dan. Questions about the material? Well, I mean, it just grows, right? When can we expect the grades? Yeah, exactly. Hopefully by the beginning of next week. I hope that everything is going to be done. It's very long to grade on the computer. Questions? Anybody about the material? How are we doing with that? We'll wait. I mean, it's still very early. What are we doing today? More chain rule. More chain rule business. And what else? Chain rule. Oh, maybe directional derivatives. Yeah, I think we'll have time for that as well. Questions, anybody in the meantime? Good morning, everyone. Come on in. Well, that will actually be part of the directional derivatives. So time permitting, we will see the gradient today. It's not that we had to change the grading scheme. It's that we're offering, I mean, I didn't see the announcement, but I think it was perhaps badly worded in the sense that we're not changing the grading scheme, but rather we're offering an alternate grading scheme where if you do better on the final, the weight of the midterm will be shifted to the final. When I was a student, this was an unspoken rule. In fact, when I was a student, you had essentially for every math class 100% final option. So if you did better on the final will be 100% of your mark. Well, yeah, I mean, exactly, right? I mean, we certainly don't want to announce that before the midterm, or else students aren't going to prepare for the midterm. Well, it's not that you're betting it all on the final, but it motivates students who may have done poorly on the midterm. It gives them a chance to do well in the course regardless. So, I mean, of course, as Tiffany suggests, you wouldn't imagine not doing any assignments, no web work, and then just betting everything on the final. That's not the point. The point is, you know, of course you want to do well on the midterm. It takes a lot of pressure off of the final. But in the case that you didn't do well, you still have the opportunity to do well in the course. So, and you know, let me mention that normally for in-person classes, right, normal lectures and in-person exams, the grading scheme is very different, right? Usually we have assignments worth 15% and a midterm worth 10%. Leaving 75% for the final exam. So usually the midterm is worth very little. Here we're changing it for obvious reasons, but normally, yeah. Well, I mean, right, I think everybody is feeling it. It's not the best situation. So, you know, we're trying to make do with a bad situation. Everybody's doing the best they can. So we're all aware of that. Yeah. Yeah. I mean, it gives you a new appreciation for in-person lectures. And, you know, I mean, in the past, students have always complained that I never record my lectures. I suspect that in the coming years, nobody's going to ask me to record the lectures. Adamar sent me an email. I don't want to push it back too much, though. But if you need an extra day or something, yeah. All right. That's Lloyd was asking how online school is from my point of view. Well, all I seem to do is work. I work. It's always work. So, I mean, the change of environment, as was pointed out, being non-existent is just as bad for me as it is. Well, probably not as bad for me, but it's yeah. No, I suspect students have it worst. I mean, I can't really complain. I mean, things are fine here, and correcting on the computer is much more demanding. But whatever. I mean, we'll get through it, and yeah. Yeah, it must be very difficult for students living alone, and yeah, like I said, I mean, it's not a good situation for anyone, but we'll make do. So last time we were talking about the chain rule. We saw one version of the chain rule, right? And well, I mean, let's recall. If you had z as a function of x and y, and x as a function of t, and y as a function of t as well. So, I mean, you can imagine plugging in those functions of t in for x and y, and so z itself would be a function of t. And then we can ask the question, what is dz dt? Not squiggly, right? The usual derivative, because it's not partial derivative. Your function would just be a function of t. And the chain rule told us differentiate with respect to x. So dz dx times dx dt plus dz dy times dy dt. That was one version of the chain rule, right? I mean, my suggestion was that you want to hit everywhere there's a t, and there's a t in both the x and the y components. A second version of the chain rule, if you have the same thing, z equals f of xy, where x is now a function of s and t, and y is also a function of s and t, right? Imagine plugging those into these. Then your function z is a function of both s and t. Z is a function of both s and t. So it makes sense to ask the question, what is dz ds? What is dz dt? And dz ds, right, you've got an s in both the first and second components, because they themselves are functions of s and t. So dz ds is dz dx, dx ds. Plus dz dy, dy ds. Very much the same way as this. And similarly, dz dt is dz dx, dx ds. Plus dz dy, dy ds. What are these s's? T's. Sorry. Let's take a few examples from the book. So this is yet a second version, if you will, of the chain rule. And now I'm sure you can extend the idea to higher dimensions. consider this. Right, so as we saw last time, you have two ways to evaluate this. You can plot this in for x and y. And you can differentiate with respect to t. Right, z is really e to the pi t minus e to the minus at over e to the pi t plus 2 e to the minus at. So you see that z is really a function of t. And so dz dt makes sense. Right, so this is a quotient, so quotient rule applies. Vu prime minus uv prime all over v squared. A is a constant here, that's right. Right, Niloy, you're making a good point here. So of course it doesn't work in this case, right? But you can think of canceling them nonetheless so that you get dz/ds in both pieces. But you're right that you would get two of them on one side versus one on the other. Yeah, as Louise suggests, that's why that trick, it doesn't really work. Let's not simplify that, but there it is. The point being that you could have done this a different way, right? dz dt is dz dx dx dt plus dz dy dy dt. And if we want to see that at work, dz dx, you can differentiate this with respect to x. And well, I mean, I don't want to do that. It's going to take a long time here. Wouldn't dy dt be round ds here? No, because your function is a function of only t. There are no s's here. Because there's an a, but a is just a constant. It's not, a is understood to be a constant here. All right. So I'll let you do the other way, the chain rule way. I don't want to do it because it's too long here. And instead, let's do one with two variables. Z is x squared sine y, where x is s squared t, and y is st. let us find dz/ds and dz/dt in two ways. Right, because I haven't proven the chain rule. Right, so first of all, if you plug this in, you see that z is s to the 4t squared sine of st. So it's easy to work out dz/ds. This is 4s cubed t squared sine st plus s to the 4 t cubed cosine st. Right, and dz/dt is easily seen to be 2s to the 4t plus s to the 5 t squared cos st. The intuition, and I mean you'll see it from here. You'll see it in this example. The intuition is that you want to differentiate everywhere there's an s, or everywhere there's a t. And let me write the chain rule. In this case, dz/ds is dz/dx, dx/ds plus dz/dy, dy/ds, right? So there's an s in both x and y. So differentiate with respect to x times dx/ds, right? Again, as you suggested earlier, if you cancel these, you get the dz/ds. And there's another one right here. Let's work out this right-hand side here to convince ourselves of what's happening. Yeah, exactly, right? It's just the squiggly d is the partial derivative, as you know, as opposed to, I don't have it here, but the regular. Yeah. dz/dx, what is that? That is 2x sine y. dx/ds is 2st. dz/dy is x squared cos y. dy/ds is t. And if you replace x with what it is, and now compare that with this one right here. Right? We have the sine st. 2 times 2 is 4. S squared times s is s cubed. And the t times t is t squared. Plus the cosine, s to the 4 t cubed. Exactly what you would expect. You don't see it very well when you're just looking at this, but think of differentiating this thing. What would you, right? I mean, if you view this as s squared t all squared times sine of st. How would you differentiate this with respect to s? Well, you would differentiate the square first. Amanda is asking a question here. Do we have the partial d for dx, ds in the chain rule, but the regular in the first chain rule? Yes, because in the first chain rule, the function was a function of only one variable t, whereas here it's a function of several variables. Exactly that. Exactly that. If you look at your function z in this way, right, which is a better way to look at it to convince yourself of the chain rule, how would you differentiate this? You would differentiate the square, right? I mean, we're differentiating with respect to s here. So you would differentiate the square, you get a 2 s squared t, and then you would differentiate the inside with respect to s, 2 st, leaving the sign fixed. Right? And convince yourselves that that's exactly what's happening here. You differentiated the x, the square, and then you differentiated the inside. Isn't the first way always faster so far? Possibly. Possibly. The problem is, very soon, these things will not be given. And then the first way doesn't work. Right? So you're differentiating the square. So you're differentiating the x squared, and then plus it's a product, so product rule applies. S squared t fixed, you differentiate the sign, and then you differentiate the inside. The inside, which was y itself. Right, so that's the good way to see it. How are we doing here? Questions? Do we want to do one more example, or are we comfortable with this? Anybody? All good? Very good. Let's consider the following then. The book introduces some sort of tree diagram. Tree diagram to help you see what's going on. Right? So if z is a function of x and y, and x is a function of s and t, and y is a function of s and t, right? So tree diagram here. Z is a function of both x and y are themselves functions of s and t. So when you differentiate with respect to one of these variables, s or t, you see that x and y both play a role. Never been a big fan of the tree diagram, but it is what it is. And in 22, they're asking you to draw the tree diagram. I know some students really appreciate that. Right? right? So that when you differentiate dz ds, well, you've got an s there, and you've got an s there. So dz ds is going to be dz dx, dx ds, plus dz dy, dy, ds, and so on and so on. Question 22 is asking us to draw a tree diagram for the following scenario. Z is a function of x, y, and z, where x is a function of u and v, y is a function of u and v, and z is a function of u and v. Right, so you've got your w here, which breaks up into three pieces, x, y, z, and each of x, y, and z are themselves functions of u and v. So again, using that same idea, if you were to ask what is dw dv, well, you see that there's a v in these three branches. So dw dv would be dw dx, dx dv, plus dw dy, dy dv, plus dw dz, dz dv. Consider the following scenario. Right. Well, Aiden, here it is. R is a function of u and v. U is a function of w, x, y, z. V is a function of w, x, y, and z. X is w is a function of s and t. X is a function of only t. Y is a function of s and t, and z is a function of only s. Let's draw a tree diagram to see what we're talking about here, and then maybe we'll discuss. So we have R. R is a function of u and v. U is a function of w, x, y, z. And v is a function of w, x, y, z. X, y. W is a function of S and T. X is a function of only T. Y is a function of S and T. And Z is a function of only S. So suppose, right? So I mean, you can imagine plugging all of these things back into that, back into that. So your function R is really a function of S and T. And we can ask the question, what is dr ds? And you see you have an S. You have S's right there. So you want to hit all the S's. Right, so right here, right here, right here. You see what's happening? So dr ds, you're going to differentiate with respect to u first. dr du, du dw, dw ds. Right, again, in a terrible abuse of notation, you can think of canceling both of these things. You've got dr ds plus dr du, du dy, dy ds. Plus dr du, du dz, dz ds. But, as you recognize, z is a function of only one variable. So it's the regular derivative, not the partial. Right? And as Juan suggests, you have infinitely many chain rules. You just got to make them up as you go along. Buffering at 1204, geez. Yeah, I guess you could factor out the dr du. Yeah. Right? So notice the regular dz/ds here, not partial. And then dr dv, dv dw, dw ds, plus dr dv, dv dy, dy ds, and lastly dr dv, dv dz, dz ds, regular derivative here. Notice there was no dr dv dv dx because x only depends on t, so dx ds would have been 0. So no need to include it here. Everybody's back? Or do some people still have an error? Very good. Thank you. Let's see an application of this. Let's see an application as far as implicit differentiation is concerned. Right? Remember, back in Cal 1, the idea of implicit differentiation, where you had not y explicitly as a function of x, but rather an equation involving x's and y's. Right, so you have this equation involving x's and y's. All equations involving x's and y's can be rewritten in this way, right? Some function equal to 0. Some function of two variables. And this implicitly defines y as a function of x. So y is a function of x. So we can ask the question, what is dy dx? What is dy dx? And to answer that, we're going to differentiate the whole equation with respect to x. Well, there's an x right there, and this is a function of x as well. So, chain rule, differentiate f with respect to the first variable, plus differentiate f with respect to the second variable, times, well, I should have said differentiate f with respect to the first variable times the derivative of the inside with respect to x, which is just 1, plus differentiate f with respect to the second variable, right, times the derivative of the inside with respect to x. Derivative of 0 is, of course, 0. And you see that dy dx is minus f1 over f2. Derivative with respect to the first variable, derivative with respect to the second. Beautiful in its simplicity. Right? Say an example. Consider this. You have this equation, cosine of xy equals 1 plus sine y, an equation which implicitly defines y as a function of x. Let's find dy dx in two different ways. First, the usual way that we encountered in Cal 1, we're going to differentiate the whole equation with respect to x, assuming y is a function of x. So the derivative of cos is negative sine times the derivative of the inside. Inside is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. Derivative of 1 is 0. Derivative of sine is cos times the derivative of the inside. There it is. Expand everything. So minus y sine of xy minus x sine of xy dy dx. Perhaps we could bring this to the other side and divide. Let's not. Let's bring this to the other side and that over there. And we get cosine y minus x sine of xy dy dx is equal to y sine of xy, and consequently dy dx is easily seen to be this. Shouldn't it be minus cos y y primed? They do. I'm bringing this to the other side, thank you. Minus. No. Wait, what have I done? Yes. Thank you. Thank you. Very good. All right, so this is the usual way, the way you're used to dealing with. Or the other way we did, using the chain rule, if we bring everything to one side, we can rewrite this as cos of xy minus sine y minus 1 is equal to 0. Right? So you have this as your function. Right? And df dx, derivative with respect to the first variable, derivative of cos is negative sine. Derivative of the inside with respect to the first variable, with respect to x, is just y. Derivative of this is 0 because there's no x, and so is this. F2 derivative with respect to the second variable, again, minus sine of xy times the derivative of the inside with respect to y. Derivative of this with respect to y, and derivative of 1 is 0. And what did we see? We saw, well, It's not an equation that I remember by heart. And it doesn't matter, because I can take 30 seconds to work it out. This is f1 plus f2 dy dx equal to 0. So it's easy to see that dy dx is negative f1 over f2. So in this case, negative f1 is going to be y sine of xy over f2, which is this, or minus x sine of xy minus cos y, which should agree with what we had right here. I mean, you could say that this is a function of y and x. Absolutely. And you're right that it was arbitrary. The answer would still agree, though. Even if you treated it this way, and I'll invite you to do it, you'll still get the same answer. In this case, right? In this case, though, if you differentiate the whole thing with, so if you have this and you differentiate the whole thing with respect to x, treating y as a function of x, you would get g1 dy dx plus g2 is equal to 0, so that dy dx is minus g2 over g1. And I'll let you finish that up, but you'll see that it's the same answer. Can we generalize? You know what f1 and f2 are. The partial derivative with respect to the first variable, partial derivative with respect to the second variable. We introduced this notation when we introduced the partial derivative. We didn't use it much since then, but it's very useful to have it. Can we generalize? What if you had a function of 3 variables, x, y, z? You see what's going on there. Right? Imagine trying to isolate one of the variables on one side and everything else on the other. Perhaps this can be done theoretically. What would that imply? That would imply that one variable is a function of the other two. Perhaps z is a function of x and y. So this defines implicitly one variable in terms of the other two. Absolutely. No, well, no, wait, Louis. You have one equation, three unknowns. What is that for? One equation, three unknowns. So you can only isolate for one variable in terms of the other two, not both x and y in terms of z. You would need a second equation for that. Right? I mean, think back to 133. If you have one equation, three unknowns, you can isolate for one in terms of the other two. Exactly that. Eloy, that's right. So here, we're not assuming anything, but one possibility is that z is a function of x and y. Or, of course, y is a function of x and z. Or, again, x could be a function of y and z. These are the three possibilities. And, of course, if you understand one, you understand the other two. So if we restrict our attention to this one, we can ask the question, what is dz dx? What is dz dy? Under the assumption that z is a function of both x and y, and x and y are independent variables. It could have been plus c, and it wouldn't matter, right? But of course, if you had a c here, you could bring it to the other side and have a new function, g, instead. Well, I mean, Eloy, you're really suggesting that we're able to solve for z as a function of x and y in practice. That might not be possible, right? I mean, it's a theoretical result. We might actually not be able to isolate. But it doesn't matter. We can still ask the question, what is dz dx? What is dz dy? And you can answer that question in exactly the same way we did before. Right? If you have this equation, you can differentiate the whole thing with respect to x, assuming z is a function of x and x and y are independent variables. What does that give us? Well, there's an x in here, and there's an x in there. So differentiate with respect to the first variable times the derivative of the inside with respect to x, which is just 1, plus differentiate with respect to the third variable times the derivative of the inside with respect to x. Derivative of 0 is 0, and you see that dz dx is negative f1 over f3. Similarly, if instead of differentiating with respect to x, you differentiated with respect to y, you see that there's a y here, and this is also a function of y. In fact, a function of x and y. So the derivative with respect to y, f2 times the derivative of the inside with respect to y, plus f3 derivative of the inside with respect to y. Derivative of 0 is still 0, and again we see that dz dy is minus f2 over f3. Second example. Is that f1 times 1? Yes. f1 times 1. Consider this. We ask, what is dz dx, dz dy? You have two options. You know exactly what you can do. What we're going to do is we're going to bring everything to one side. And all I'm going to do is I'm going to do it using implicit, using the chain rule, using this result. So f1 is ln y. f2, z plus x over y. f3, y minus 2z. So dz dx, according to this, is minus f1 over f3. So minus ln y over y minus 2z. And dz dy is minus f2 over f3, which is minus z plus x over y minus 2z. Somebody's asking if there's a reason why f2 does not appear in the derivative with respect to x. And there's an excellent reason, right? I mean, here you would have an f2 times the derivative of the inside, but x and y are independent variables. So dy dx is 0. Exactly as Louis suggested. Right, so here I did it using this implicit differentiation theorem, if you will. You could, of course, simply differentiate the whole equation with respect to x, assuming x and y are independent variables and z is a function of x and y. The result would be exactly the same. How are we doing? Charles is suggesting that it would be simpler to identify the partial derivatives by the letters. The problem is that sometimes it's not. Sometimes it's not easier because suppose you had a function of x squared and y. and you want, so I mean, suppose you have this is equal to 0, and you want dy dx. So here, of course, this defines y implicitly as a function of x. And if you differentiate the whole equation with respect to x, it's tempting to say fx, but now we're in trouble. It's actually not fx, but f of x squared, and that's why it's better to write f1. Yeah. Right, so I mean, just to finish that up, if you will, the derivative with respect to x, you've got an x here, so f1, fx wouldn't be correct here. Derivative with respect to the first variable times the derivative of the inside with respect to x. And then plus f2 times the derivative of the inside with respect to x. So you see this f1, f2 notation, very important. I'm going to leave it for a moment. Questions here? Let's move on. Let's move on by moving back to limits. How do we know if x and y are independent or not? Sometimes it says in the question, sometimes it doesn't. So you have to be aware of what's going on. You have to have an understanding of what's going on. If nothing is mentioned, you have to pick it up from the environment. What do I mean by that? Here, you have this equation. One equation involving 3 variables. You're thinking to yourself, theoretically, I could isolate one variable in terms of the other two. The other two would be independent. Nothing is stated, so you assume the most general case, namely that they are independent. If y was actually dependent on x, they would have had to tell you to begin with. There's no way for you to know that that would be the case. Let's go back to 2D when we were importing or generalizing the notion of limit. Let me know when you're back. Is everybody back already? Back, very good. Almost back. All right, thank you. Right, so I mean, we saw one big issue with limits in 2D, right, as opposed to just on the real line. On the real line, there was only 2 ways to approach the point. In the xy plane, though, there were, in fact, infinitely many ways to approach a point. So this was the issue with limits, that you had to check all all the ways to approach the point. So, I mean, we absolutely needed the epsilon delta definition here. However, so that was for limits. But when we moved to the derivative, suddenly we were back to two directions, namely the rate of change in the x direction and the rate of change in the y direction, not any other direction. Why not? Can't we ask the question, what is the rate of change of the function in some other direction that is not the x or the y? Can we extend the notion of rate of change to some other direction? And if so, how? So not just in the x direction or the y direction, but any other direction. Any other direction let's say a direction given by a unit vector. AB. So definition. Given a function f of xy, we define the directional derivative of f in the direction of a unit vector. Denoted du of f to be the limit as h goes to 0 of f of x plus ah, y plus bh, minus f of xy over h. Observe, if you will, that this is really an extension of the partial derivative. Because if u is the vector 1, 0, then this is what? If A is 1 and B is 0, this is f of x plus h y minus f of xy over h, which you recognize to be the partial derivative with respect to x. If v is the vector 0, 1, then this is f of x, y plus h minus f of xy over h, which you again recognize to be the partial derivative of f with respect to y. So this directional derivative really is an extension of the partial derivatives, right? The partial derivatives are a special case of this directional derivative. And now let's look at this limit. Let's look at this. And assuming your function is continuous, what happens? If you plug in h equal to 0, this is going to be 0, this is going to be 0, so you get f of xy minus f of xy, which is 0, over 0. Assuming your function is continuous, you have a 0 over 0. What are we going to do? L'Hopital's rule. If you apply L'Hopital's rule, differentiating with respect to h, observe what happens. Well, you've got an h in here, and you've got an h in here. So the derivative, f1, times the derivative of the inside with respect to h, right? And now you recognize the importance of the f1 notation, right? It wouldn't be fx. You're not differentiating with respect to x, you're differentiating with respect to the first variable, which is x plus ah. Juan is asking how we are doing a derivative using L'Hopital's rule to compute a derivative. Well, never mind that it was a derivative, right? I mean, of course, you recognize that this is duf, but put that aside, we have defined duf as this, and now we're just evaluating this limit. We're just evaluating that limit, and that limit has the form 0 over 0, so we can use L'Hopital's rule. So we're differentiating with respect to h. H is the variable of importance here. You've got an h in the first variable and in the second. So f1 times a plus f2 times the derivative of the inside with respect to h, just to b. This doesn't depend on h. Derivative is 0. Derivative of h is 1. And now, assuming f1 and f2 are continuous, what do we get? This goes to 0, that goes to 0, so we get F1 times A plus F2 times B. And you can actually rewrite this in a nice closed form as F1, F2 dotted with the vector AB, which was our original vector U. So this motivates the following definition. Given a function of two variables, we define the gradient of f. Denoted gradient of f, or nabla f, to be exactly that. This F1, F2 business. So a directional derivative is the projection of the partial derivative vector. What I would refer to it is the rate of change in the direction of the unit vector. Let's not think of it as a projection. Let's think of it as the rate of change in the direction of u. Divergence and curl will not be covered here. No, only gradient. Let me point out that this generalizes to higher dimension. Generalizes, right, gradient of f can be f1, f2, f3, and however many that is 264 material, that's right. Well, nothing is stopping you from taking 264. It's a great course. Everybody should take 264. How hard is it compared to this? It's not harder. Not harder. It's just different. It's just different, and you have immediate applications to physics. If one of the partial derivatives of the gradient is 0, I guess, what happens? Nothing. Nothing happens. That's just it. Let's take a few examples. I'm sure that will come up at some point. Yeah, 264 is very interesting, right? The thing with 263 is it's sort of a transitional course where, you do a few things to allow you. So, I mean, you're just extending calculus to higher dimensions. In 264, you're really doing one thing, namely calculus on surfaces. There is no real difference between calculus and calculus for engineers. For some reason, the engineering department wants courses just for engineers. There's no difference. Sometimes there's one topic different, but for all intents and purposes, there's no difference. Consider this, we are looking for the gradient. Let's calculate the gradient. I don't know about kryptonite. There are some subjects that I did not spend enough time studying. That's the only thing. Really, that's my only regret. That sometimes I did not take the courses seriously enough, and I should have studied more. There it is, right? Gradient, the derivative of this with respect to x as the first component, the derivative of this with respect to y as the second. Well, no, I mean, that was serious enough. When I was doing 2 textbook worth of exercises, that was serious enough, but there are other courses where I did not do that, and I probably should have. I've rubbed it off now, but we said, what did we conclude? That the directional derivative of f in the direction of u was actually the gradient dotted with u. Nandini, nice of you to join us. We're doing calculus 3 here. We'll do a few exercises. We are at the end of the lecture today. What is the question asking for here? Rate of change. Find the rate of change of f in the direction of f at the point P in the direction of u, where f is the following function, x squared e to the y, the point P is the point 3, 0, and u is this vector. Yep, page 1005. All right. First of all, the first thing to make sure of, right? I mean, this definition here is very dependent on the fact that u is a unit vector, right? And here, 3 over 5, 4 over 5, I'm sure you recognize that this is a unit vector, right? This is 3 over 5 squared plus 4 over 5 squared, or 9 plus 16 over 25, which is so unit vector, we're good. And take a moment to calculate the gradient. Gradient 2x e to the y, x squared e to the y. Gradient at 3, 0, when x is 3 and y is 0, what do we get? 6, 9, and the directional derivative at the point 3, 0 is the gradient dotted with your unit vector. Gradient is 6, 9. Unit vector, 3 over 5, 4 over 5. So what is this? 36, 46, 56, 54 over 5. Thank you. Minus 4 over 5. Minus 4 over 5. So that's going to be very different. Minus 36. So 16 minus 18. Minus 18 over 5. Thank you. Exactly that. All right. That's actually all the time we have for today. We'll pick this up again on Thursday. Why did we get the norm? This definition here, the directional derivative is very dependent on the length of the vector. In the definition of directional derivative, we assumed that we had a unit vector. So you have to be using unit vectors. If you use vectors of different lengths, you get different answers. Yeah, I mean, it's questionable why they're not accepting Cal 3 from CJEP. I think you do most, if not all, of the material. I mean, let me ask you this. Was sequences series done in complete detail with Maclaurin series? And what about partial derivative and double and triple integrals? Double and triple integrals as well? Polar coordinates? So if all of that is done, well, certainly everything we've seen so far, yes, but multiple well, so I mean, if it's all of that, seriously, it should be credited. So as people have suggested in the chat, maybe discuss that with the dean. Yeah, I don't know that we'll have time to do parametric curves here. Perhaps at the end, or not. But that's where 264 begins, with parametric curves. Very nice. Yep. Jacobians and so on. Well, so seems to me that you've done all of this. Well, you should be doing very well. Should be an easy A then. Very good. So thank you all for coming. But I mean, you know, I'm going to encourage you to speak to people in charge and see if that can't be credited in subsequent years. Very good. So thank you all for coming, and I will see you on Tuesday. No, Thursday. You guys have a good one.